try to do it first.
Okay, you're a little bad on the Monday after a test, all right? So just work with me here. We knew there'd be a drop. The last time it was 85, so it was a drop. 4 points, whatever, not a big deal. So it didn't go well. You've already heard about it. I've also done something else. Is you'll find that because I don't use Blackboard, I add a little strip of paper. It has all your grades on it. So that way you know what your grades are. You can double check them too. Right, in case I accidentally wrote down, slip of the finger. Could happen, so double check your grades, all right? So I don't think there's any problems, but I definitely would like you to check for yourself and for me. Also, because some of you got A's on the test and are still failing. Because you didn't turn in any homework, you're failing. So you need to know that, right? The homework they said, any one isn't a big deal, but we're almost done with them. Right, remember, Wednesday, next problem set. So your homework scores are largely set now. And remember, any one was not worth much, but they add up to a test. And that average is pretty much known at this point. But we do have 3 more, 8, 9, 10, 3 more problem sets starting Wednesday. So I'll give those back if you're wondering how we did them so quickly. Because of meetings I have all week, I wasn't going to be able to get to them until Friday, talk today. So I did it myself over the weekend. You know that cat meme, it's like scratch me, that's a little more. Yeah, so I did do them myself, so come see me. Now, I actually tend to be pretty accurate, but there's no way I can make mistakes. So adding them up, I tend to care a bit more than my TA, to be perfectly honest. So I was very careful. It also probably helped that you had one person grade the whole thing. I think I was more consistent, but you can check that too. I don't think I was perfect, so in case you know, hey, I did the same thing as Johnny Joe, and he got 3 points and I got 2, that's me screwing up. So you and John, to show me Johnny Joe, and I'll mark him down. I'll mark him down, but I did make some mistakes like that, so double check. It won't be a point or two, and I may not have added them up, and I may have missed a question, I may have skipped a page, so definitely check them out. So anyway, the reason is you guys are doing pretty well, but the drop date's Friday, so in case you're not sure, then, well, there you have it. So, anyway, any questions? Are we okay? I know spring break's next week, and most of you get more hours in your class, right? In your job. But any questions at all? So we're okay. All right. So I will end a little early so that you pick these up, and so we're done with that whole. Henry's Law and Radius Law, sorry. We did actually legitimately finish that. In terms of what you'll see again, final, maybe. I've never been big fans of Henry's Law or Radius Law because they're pretty massive approximations and I hate that. Will it be on the final? Of all the subjects I'm likely to not put on there, that's it. I can't guarantee that, but then again, we'll have to review for the final. I'll let you know whether I put it on there. But just recall that, let me just erase this. Let me just recall that delta mix. Now the point of this, the reason I went over it, I really had to, don't even write this down, right? Now, in the ideal case, not ideal dilute. Some of you messed that up on the final on the last exam. There was a question about ideal versus ideal dilute, and some of you got the two mixed. Okay, so the important thing is that all right, this is entirely entropic because there's natural logs, and so remember this is ideal. Not ideal dilute. If it's ideal dilute, then this guy, the solute, is an Henry's law constant. So the important thing is that the chemical potential, or the delta G per 1 mole, which is delta G from the back of the world, it has to be altered when you're in a mixture. Now, if you're going to get things to react, you have to mix them first. Either liquids A and B react. Generally, you don't do that. Generally, you have materials A and B reacting in solvency. Regardless, their G's from the back of the table, the back of the book, are now different as soon as they've been dissolved in a solvent. And that's kind of horribly important to take that into account. All right, now there's going to be actually, these terms here are actually going to be altered even further, because now we're not mixing water and ethanol, which doesn't do anything really, unless you drink it, which is fun. It's when A and B react, right? So when A and B react, we're going to actually change these terms a little bit further. So that's kind of the point, is that, well, it's obvious, right? The mole fractions are going to change when things react, and that's where we're going with this. Once we finish this section, so we're going to talk about reaction G's, why reactions don't go to completion, why do reactions have finite yields, what is the yield? We'll do that for gas phase reactions, because just like in everything, it's easier to do gases, and I'll point out how to do liquids, but we won't go there. Then we'll cover batteries, and that's pretty much the class is over. We'll still have class, all right, because that's about 2 weeks. We'll still have class, but we're going to mop it up with a couple of random disjointed things that I don't like too much. Making test 3 easier. However, the fact that there's not a lot of coherence to it, sometimes gives problems with test 3, and sometimes people don't do so well on test 3. It often is people's worst test. But it really is actually the easiest test. It's just not as thematic. So just be careful. We're almost done. We're 1/3 done with this class. So just be careful on this 1/3, because while we're still rolling with our delta G's and whatnot, we're going to move away from it for the last half of this section. And it gets messy. And messy sometimes is hard to follow. Anyway, okay, blah, blah, blah. I'm just running my mouth. All right, so let's start talking about... Okay, that's mixing. Now that you've mixed A and B together, now they react. Now remember, these things are stoichiometric coefficients. I think that's the proper term for them. Maybe engineers have a different one, which actually makes it harder for you, even though you've seen this stuff before, but that's what I call them. Stoichiometric coefficients. And I'll make this a very generic type of chemical reaction. About as complex as you would ever run into. And remember that we're going to be in delta G land, because that's where 99% of anything that ever happens ever. Obviously, if anything in the natural world. And so I have 4 things, so I have to sum from 1 to 4, and they have the chemical potentials, and of course they're actually going to change their mass, because they're going to react. Now remember, we're at constant T and P, which makes delta G. Actually, this is the answer to a question that almost everyone missed on the last exam. And this got brought up in class. I'll go over the exam on Friday, point out what you did, what you didn't do, because there were a couple of pretty spectacular screw-ups. So I haven't posted the answer key yet, because I wanted to make certain it was perfect. I'll post it right after class. Sorry about that. And remember, please look at the answer key before you ask questions. It's just easier for us both. Okay, constant T and P. Okay, these are gone, and you're left with this. And remember, okay, a question that almost everyone missed on the test was, I said the change in A at constant T and V is negative, means something is spontaneous. Half of you said no, it's 0. You ignored this. Remember, we went over this in class. So half of you missed that question. That was a true and false. And the answer is that just because you hold natural variables constant doesn't make the thing automatically zero because you got this thing left. So change in A being less than 0 does mean something is spontaneous if T and B are constant. T and P are constant, delta G has to be less than 0, and that's because this term remained. So it's something you guys universally missed. Half of you missed, sorry, that was pretty bad. Remember, whenever in class, if you missed that question, what you need to do, watch the videos, right? Because that did get brought up. And anyway, okay, so here's our change in G. Remember, I can just divide by number of 1 mole, and it becomes a chemical potential. There you go. Now, I'm going to genericize this by calling something, let's call this an extent of reaction, and it'll go from 0 to 1. 0, nothing's reacted. 1, it's fully reacted. And that makes the change in A. Okay, this is kind of boring. Okay, now, here's a funny thing. This parameter will describe how A, B, C, and D react. So I'm going to need a minus sign for A. Okay, yeah, sorry. All right. So, if this reaction goes to completion, let's mix A and B. This is 0, nothing's had time to react. That means that there's been no change of moles in A. Now, if the reaction goes to completion and this is 1, then I've lost however many moles I added to begin with, right? And now remember, if this is like 2 moles of A reacts with 1 mole of B, sometimes people in PChem, they play games where like, well, they'll set up reaction conditions when we actually start doing calculations on reactions. They'll give you 1 mole of this and 1 mole of that. In other words, it's already complicated enough as it is, as you're going to see. It's already complicated enough as it is. Sometimes people who teach PChem will complicate it further by giving you a limiting reagent, right? And that would be A in my example. I'm not going to do that. That's why make something complicated a little bit more trivially complicated. So anyway, just in case, I will never, when I set up reactions, I will always give you 1 mole and 2 moles if that's exactly how it reacts. So in other words, that's one way I'm not going to trip you. Okay, now this is awfully boring. So I'm just going to do C and D. I think you get the point, and of course, the products are forming, so there's no reason to say that there's a negative change. And that's, of course, because I'm not going to look at this and then in my bucket, or better yet, a flask. I'm not making meth after all, although I do know how. I'm not going to throw A, B, and C, and D all in at once, right? If I'm doing a chemical reaction, I'm going to add A and B, and only A and B. So, all right, now if this is the case, what would that allow me to do? I actually recognize your voice, by the way. Yeah, I heard you. Anyway. Okay, so there's this. And I have painted myself in the corner, haven't I? Let's see how far I can go. I hate it when I do this. It just hurts me. Okay, and you may recognize this is actually the change. Oh, I barely made it. There we go. How is this going to do anyway? Anyway, I hope you can see that. If not, you can see the video. And what that means is that, therefore, because I got a slope, and you know how much I like calculus and derivatives. And look what I got. I got a change. I've got the formal definition, the Hess's law thingy for chemical potentials of products. Right? See, I've got products minus reactants. And sort it in a funny way. So that's why that's kind of useful. And let me show you what I'm going to be leaning towards here. And again, remember, so table in the back of the book, right? Those are the formation delta G's. And even though it's not the absolute, I'm not writing them as formation G's. It doesn't matter, right? References, whatever your common reference point is, it doesn't matter. All things are relative. So in the table in the back of the book, remember that the formation G's are G's per mole. That actually means that they're actually chemical potentials. So again, so that just means that this is actually calculated from the table in the back of the book by Hess's law. It's why they have Hess's law on the second test. It's going to be on the third because we haven't gotten rid of it yet. Okay, so to emphasize that, let me screw up my notation. G per mole. I know I shouldn't be doing that. I'm messing with my notation because I've already been writing it. And let's do this extent of reaction, not a change, just the extent of reaction. So it'll go from 0 to 1. And here's what we're going to see. Now, you're going to figure out exactly why. You're going to get things like that, where the slope, here the slope is negative, right? So that tells you how much your reaction is going to go. When we do batteries, this initial slope, okay, I haven't quite done it at the initial point, but you get the point. The slope up here is actually going to be related to the battery voltage. And we like to work with fresh batteries. So that's why that's important. But now, what's important here, okay, if I was a synthetic chemist and I'm here, what do I say? My reaction begins with D. It's equilibrium, the reaction is done. Here's my products. Whatever here, if this is 0.75, I got 75% products, right? So now this is why reactions go to completion. Okay, some more terminology, and I'm going to connect you back. I already mentioned this once, talking about equilibrium constants and reaction constants, so let me get to that. Okay, so now, per chemical, okay, sorry, shorthand. I want to start thinking about how the chemical number table in the back of the book changes for A versus B versus C versus D, rather than, again, per G per mole, which is chemical potential. I want to think about them individually, not as a whole for now, but you do need to think about them as a whole. And remember, this is activity. And remember, activities are really good when you're talking about real things, which is I add 1 gram of chemical A, 1 gram of chemical B to 100 mils of hexane. All right, that's how you do things. In which case, we want to be using activities, because Raymond's law is really not a good idea. And that's actually why when I actually have you doing calculations, I'll actually have you do gases, because that way you don't have to mess with this. But you know what you do when you go to real things, you deal with activity. Okay, now that makes, therefore, delta G. Right now, I'm going to add this term, delta reactant G per mole, which is the same as chemical potential. So I'm going to slip between chemical potentials and G per mole because they're the same thing. I do it a lot. I'm kind of following the book, and that's what they did. I probably should stick with one or the other. I'm just kind of bad about that. Okay, I've got 4 things in my example. We've got this guy. Now remember that this term, and we've got another term. Okay, again, G per mole is in the back of the book. This is, and I've got the standard state. Okay, this is your Hess's law deal. When we were doing Hess's law, and I said A, B, and B goes to C, and therefore A goes to C, this is that part. But when you did that, when you're talking about A going to C, that was valid for when you have a pot of A, and you're just waiting now for it to turn to C, but it hasn't done it yet. In other words, this is time 0. But then time passes. And as time passes, as things go and come, activities change. Right, so Hess's law is time 0. This is what happens later when the actual reaction starts to occur. And since this is per mole, I'm going to do this. I've got my stoichiometric coefficient. Activity of I. There we go. Okay. So now, the thing is, well, you've been doing this in high school. Now that's the hard part. That's where this actually gets more difficult. Now you did do a little bit of this in freshman. You may not recall, or maybe you took freshman somewhere else, and you were just kind of fed these equations without knowing A, where they came from, and B, They actually, as I warned you, the equations you learned as freshmen were wrong. They were simplified. We're told that they were incorrect. So now we're going to get them right. And anyway, so now this part's easy, but what about this part? So I'm painting myself into a corner. Here, let me do it like this. Sorry, just so that, I don't want you getting lost in your notes. It's just that I have to write all this out. Okay. So again, just some derivations. Okay, sorry, I'm using capital letters. Sometimes I screw it up. Activity of A. Okay, that's going to be minus. Right, remember, okay, why am I making this minus? The same reason I did up there, because A is going away. So don't forget, it's just simple. Because I could just say that I could just add a minus sign up there and it would go away, or I could just define this as being negative, or I could just put a minus in front of it. That's just a lot easier. Okay, same for B. B plus C. You see why I need that for room. All right. Now, here's the thing. ln A plus ln B is equal to ln A times B. Right. Minus ln of A is ln 1 over A. Right. Okay. So this is all equal to ln activity of A minus its stoichiometric coefficient, activity of B, its negative stoichiometric coefficient, and then C's are all normal, and sorry, products are normal. Okay, and there you go. Okay, therefore, now I'm going to get back to this. Sorry, I'm another therefore. G per mole, again, that's the same thing as the Hess's law deal. RT, ln, oops. Okay, now let me write this in the way that you are probably more used to. As you probably saw, it started to remind you of freshman chemistry. A to the C, B to the C, A to the D, B to the D. And now I'm going to write A's on bottom. Reactants on bottom. It's A and B. There we go. All right. So, look familiar? Remember your God, what do they call it? Not solubility quotient, but anyway. Delta G naught plus RT ln K or Q if you're at equilibrium, right? Where these were actually concentrations of products over reactants. Right, you remember that from freshmen? Yeah, a lot of you do. You know what was wrong with that? All right, there's actually a reason I'm doing A, B, C, D. In other words, I'm having equal moles on each side. If I had, say, 2 products in one reactant, I've got natural log of what? Natural log, give me a unit. Concentration. I've got A goes to B and C. B, C, A.
Natural log of concentration.
I had natural log of molarity. One fundamental thing I hope I've got through to you is that you cannot have natural logs of things in units, because you can write natural log as a series, and then you've got that whole problem with the sum with 1, which is no units, plus something with units, plus units squared, plus units cubed, and that simply does not work. So when you properly write this out, and you do your reaction quotients, K or Q, whichever one you want to call it, I see both, this has to be unitless. And the way they taught you in freshman, it was not necessarily unitless. And that meant that it was not necessarily correct. They simplified it because it was easier for you to understand, but all your numbers were dead wrong. So I kind of hate that we do that, especially because I have to fix it. It's not fair. So anyway, all right, now let me actually start using it for real situations. And I'm going to actually go back to gas phase. Because I know what activities are for gas phase. They're partial pressures. And that's easy to understand, partial pressures. It's something that is, you understand partial pressures. That's not hard to put in your head. activities, I really don't even know what they are. I mean, they don't even have units. They're related to concentration, but they're not. They don't have units. Concentration has units, so I know that there's a fundamental disconnection there. Okay, so let's do examples. And again, gas phase composition. Let's make gas A go to gas B. And gas phase reactions, like that includes that one we had last homework or 2 homeworks ago, steam reforming to make hydrogen. We make hydrogen by steam reforming. We take that hydrogen and we use it then to make ammonia. Ammonia is made, remember that's the second most produced chemical in the world, so it's pretty relevant and is made in gas phase. And it has catalysts too. I'm not going to talk too much about catalysts. You actually get that at 346. Okay, then let's do the reaction G for mole. And that's just going to be the chemical potential of B minus the chemical potential of A. And again, let's break this down into individual parts. Okay, so here's the part for B. Now, I'm going to define activity. This is technically the definition of activity. It's just that, all right, so remember activity, when I sprinkled powder A and powder B in hexane, this would be the partial, so I had that in hexane and I want them to react, and above it, in the vapor phase, I have a little sniffer that reports to me what the partial pressure is, and I already know what the pure partial pressure is because I measured it before. All right, so I can do this for my powder in a solution as as A turns into B. But that's actually kind of a BS thing to do, and it's not really even feasible. If I'm doing a gas, then this is perfect. It's definitely activity, because that actually is the definition of activity. And when I said that this was a mole fraction of B times the pure partial pressure, remember that was an approximation. That was the ideal approximation, which is actually kind of pretty badly wrong. So don't forget that. Now let me subtract A. I'm going to do it like this, because this way you are reminded of what the individual energy parts are. Again, I'm going to use the absolutely correct definition of activity. I'm going to have another bracket. And now I've got, again, the Hess's law part. Again, that's why I'll have it on the third test and didn't include it on, did not include it on the last test. So I'm just putting all the natural logs together. I'm just basically doing what I did before, except I've got a base to it. And again, the point here is that you can't have units. This is really the proper way to do this. And whether I'm talking about gases reacting or what you actually do in your class is take powders and add them to solvents, you can use a sniffer above the solution to measure these partial pressures of these chemicals you've added, and then you've got perfect numbers. It's just that the example of powders in solution, you're not going to, it's kind of ridiculous, because you're not going to get a little mass spectrometer, which people do this sometimes. You're not going to put a little mass spectrometer over a vial, measure partial pressures, just to measure activities correctly, because it's just kind of stupid. Okay, now what I want to do is decompose this into parts, and again show you why things react to it to a certain extent. Okay, let's do this part. Okay, I'll call that 1, and we'll call this 2. So that way you don't get lost in your notes. Okay, let's do 1. I'm just going to graph it. And these are G's per mole. And we're going to do this as a function of reaction state, an extent of reaction. This will be A, and this will be B. So 0 equals all A, and 1 equals all B. So A is going to be decomposed to B. And these are G's. Okay, because I'm doing this part. Now remember that when you did this part, it actually changes, right? This is the time 0 component.
So if I said, how much G do you got, and again, there's a delta because it's a formation G. How much G have you got when you fill the balloon with A? And you fill it with a mole of A, right? Because I'm going to do it that way because it's easier. Well, you look at the table in the back of the book and you're here. Now, A decomposes to B. And if it decomposes all the way, then the G component in the balloon is no longer A's value, but B's value from the table in the back of the book. Now, remember how Hess's law works. If I've got A goes to B and C goes to D and F and all that garbage and jazz, but if you had to scale one of them, then the H and G scaled as well, linearly. So if I had to have twice the reaction that balances Hess's law, then the numbers I added up would have doubled. That's a linear scaling. Blah, blah, blah. What it means is I draw a line. Right. And again, I know it's just a straight line. This guy had a higher G than that guy. I just decided that that was the case. And anyway, so there you go. It's just a straight line. Okay, now let's do the second part. And I'm going to call this is actually really a mixing component. Kind of. I'll call it that for now, then I'll point out where it's not quite the same thing. So this is 2. So, yeah, let me just tell you real quick. I see a natural law, so I know this is entropy. And I know when I was doing this thing, when we were talking about Henry's law and Raoult's law, this came from entropy. And what's different is the reason that, the only thing that's different here is that A is actually disappearing. So A will form B, and A will mix with B, and that's good. That drives the reaction. But the only difference between Henry's and Raoult's and all that other stuff we've been doing is that A consumes itself in the process. So it's a funny thing. This guy actually is a little bit more complicated than it looks because A is changing and so is B. It mixes things together, which is helpful, but you're also losing it, which is not. So this is mixing with a twist. Again, that's because of the reaction. And I don't know what these numbers are. I mean, I can look them up in the table in the back of the book. But this would be 0 initially if once I have all A. Sorry, I know I'm too OCD sometimes. It just bothers me when I see things too close together. But I know sometimes you folks get confused. So I know that things like to mix. Things like to mix. But you don't get any benefit if A doesn't form B because there's nothing to mix with. Here, you've got a 50-50 mixture. That's very good. That's entropy. And delta G has an entropy term, minus TS. So gaining entropy is good. Minus TS, T is always positive. And if you go all the way, though, see, once you get past there, you're actually starting to hurt yourself. Because now B is taking over and B doesn't have any A to mix with. So the point of this is that you get this, right? I sum these together, and if I sum the two graphs, now look, there's no little circle, Sorry, my little unsymmetric. I would normally take this. I'm going to take this line and I'm going to droop it with that line. And so that's going to look something like this in this example. And again, here, DG, DE, I'm sorry, I should have delta. Let me just do it. I hate it if you get confused in your notes. Right, X marks the spot at that point. Now, remember, if this is true, what is the difference in chemical potentials with C and D minus A and B? I'm sorry, I'm doing A versus B. What's the difference in chemical potential of B minus chemical potential of A at this point? Noting that they change continuously this way and this way from the number in the table in the back of the book, right? So what is it? What's the difference in chemical potential of B versus minus A? If the slope is 0. Right, 0. Right. So therefore, at this point, this is what I mean when I do it like this. Chemical potential of B is equal to the chemical potential of A, and the reaction stops. So, there you go. Now, some reactions do go to completion. So why? Okay, this is actually going to help you. I just remembered right now what was the question that a lot of you used on the test. And actually, I asked it because of what I was going to talk about now, although I had covered the material. I just was foreshadowing sometimes in my question. You don't have this. Okay, now let's do an example of a reaction that does go all the way. So let's call this a better reaction. In terms of its thermochemistry of A going to B working better, I've still got the mixing. You see, this isn't going to change much. This isn't going to change much. What can alter this component would be the number of players. Do I have A to B or A to B goes to C and D? That will change like how much this goes up and down. And the stoichiometric coefficient. So this little dip here, you can't do much with it. You can bend it around a little bit, and that's because of the nature of the reaction. But for the most part, it really looks like this. Now this part is malleable. From the back of the book, the Hess's law part. Boom. Right? Now when I'm trying to draw, I'll even better. Don't erase what you just wrote. I'm trying to get it across what's happening. Right. A big drop in the sum of the two. Sorry, I'm using the word today. So added together. Okay. Here I'll dot. I'll dot that other component so it's kind of more obvious what I'm doing. Okay, so the point here is things like to mix, and once you get past 50%, it's not helping you anymore. So even if A goes to B is not favorable in terms of Hess's law type question, if you get a positive delta G, the reaction will still go forward because A will decompose to B just to mix with it to some extent. So imagine if this example was turned upside down. It actually would work, just not very well. Now, okay, so that's a delta G plus. A delta G minus can either not go to completion or go to completion. It just depends on how strong this component is. Right. This guy says don't go past half. This guy said no, I'm going to overwhelm that part. All right. Now remember that this is the entropy component because it's a natural log function. Whenever it's a natural log, I know I'm dealing with entropy, and this is just the pure H. And the pure H overwhelmed the entropy. Now, what do you think that means, though? And this is the answer to a question that a lot of you missed on the test. All right. So now what? All right. Let me remind you what the question was. A goes to B because the entropy of the system plus surroundings increased. And a lot of you said, no, that's not true. It is true. The total entropy increasing is what makes everything happen, right? That is the supreme commander of the world. I worship chaos. So anyway, certainly sounds bad, don't quote me. So this is the entropy of the system, and it's being driven to completion, which is technically bad. It's not helping you. It helps you up until this point, then it just kind of went away. Okay, now knowing that the total entropy is the biggest thing in the world, how did this go to completion? When the entropy of the system at first was helpful, but suddenly it didn't help at all. What compensated? Enthalpy did what? Now remember, entropy. You have to tell me total entropy increased. And the entropy of the system didn't do anything. Ultimately, when it went from all A to all B, I had 1 mole of a pure gas and I had a different mole of a pure gas. No entropy change. Or very, very little, all right? Now maybe there is some because the perfect gas equation is perfect, but anyway, basically the same entropy of the system. You said the enthalpy did it, but the enthalpy did what? You have to express it in terms of entropy. There's the inside plus the outside. So if it released a lot of heat, Surrounding entropy increased, right. So the insides didn't change, but the outside did. Right, this is a reaction that got hot. It got so hot that the outside entropy increased so much that it overwhelmed the inside entropy. Right, so again, that's a question a lot of you missed. I was a little taken aback by that, but just you won't make that mistake again. So remember, it is very kind of confusing. I kind of hate this. You've often been taught that there's the H and the S component of the delta H minus T delta S. Remember that delta H, because we do everything at constant temperature and pressure, especially when you were freshmen. We didn't tell you that, but that is what you were learning. That H is actually just telling you how much the entropy of the outside changed, and that minus T delta S, there's no subscript on the S, that's the system entropy. So that is an expression for total entropy, times minus temperature. So now actually, I got a little bit of time. I want to express this another way with a graph, and then ends with about 2 or 3 minutes to spare, so you can spend the time to the test. Now Friday, I'm going to go over your test, so when it comes to regrades, please maybe wait until, well, look at the answer key, which I'll post as soon as I get back. Sorry that was late. I wasn't able to work on Saturday. This is actually a bathroom broke, so bathroom here, they turned them all off, so I didn't get a chance to post it. So maybe wait till I go over the test, because there were some things I do want to make certain that everyone understands. And that's next Friday. Friday after that, because this class does get a lot easier, we do want to learn the 346 stuff, right? Right. Oh, yeah. I want to prep you for 346. The material we're getting into, once we get past this stuff, is so easy, there's not anything to talk about. So I'll do 346 stuff, but let me do 346 stuff now. Besides, it's a really good explanation for how this works. So this is population. These are quantum levels. Population of A, population of B. Okay, so we're getting back to quantum levels. What's wrong with me? And this is also at the same time increasing energy. Okay, now there's energies, and then there's a state with that energy. That's quantum mechanics. And we're doing A goes to B. And this is a reaction that doesn't work. You might want to write that down. So again, there are certain quantized energy levels, and they may correspond to how fast the molecule is translating and whatnot, or rotating. Okay, here's A. And now here's B's. Copy this one. Okay, so again, and now the population means that, what this means is that, again, this is a certain rotational translational state that has this amount of energy, but it has temperature too. This will be a room temperature. It has to, that's money, and it has to spend it. It's not a Republican. So it spends it. That was me. I'm not supposed to say that stuff, by the way. It's just one of the people actually hoard money. That's why it's not good for wealthy people to get super wealthy, because they tend to put their money in a bank, and it actually hurts the economy. So that's true, economics, right? But anyway, so it has money, which is energy by a form of heat, and it has to spend it. It has to use it up, it has to spend it, and it does that by occupying these higher energy levels. That absorbs the heat. It has to do something with it because it's hot. Now, it just turns out that A has lower energy states than B. And they're populated. And of course, again, there's variations in population. Actually, this curvature, you'll actually calculate that in 346. It's one of the first things you'll do. So, now I'm looking at this and I see that A, if A is going to go into B, that's not great because A has lower energy. A has a lower energy state than B. And so I'm looking at this and I feel pretty strongly this is endothermic. So this is an endothermic case. Because A, I'm going to have to kick A in the pants to turn into B. I can see it doesn't want to do it. It wants to hang out here. And so for me to get it up there, I need to heat it up. So this is obviously an endothermic case. For A, B, bad. Call that bad, okay? You don't even have to write that down. But you know endothermic reactions kind of don't tend to want to have it. Okay, and again, this is a quantum energy level. All right, at the same time, some endothermic reactions go to completion. An example, salt dissolving in water. Now, I'm pretty damn certain that works really freaking well. All right, and I'm not talking about saturating it, I know I can do that, but if I take some salt and I have a pool of water and I throw it in, that stuff's gonna dissolve, no problem. But why? Why, if this is the case? This is really kind of cool. No matter what, this is endothermic, but when salt comes to water, you see we have this happening. We have more states, more different little micro states available to live in, right? And that affects the free energy, which is the other term for delta G, just as much as anything. There you go. Now what happens is that when I push A little bit with some heat to sit in these higher occupied states, what happens is they wander into B space. I'll draw this for all of them. Okay, again, the A that has enough energy to react, oh god, those look awful. Anyway, they're flowing into B. The A flows into B. And here's the thing, there's so many microstates, it gets lost. It's seriously, it's somebody walking in the woods and you get completely lost. And if you're disoriented enough, you'll never find your way back to the road, right? And that's because the forest is very large. And that's the same thing as saying you have a lot of microstates. This is the thing that drives endothermic reactions to work. It's the entropy, which is the number of microstates of the products. So anyway, just another way to see things. And again, we'll go into more of this next time. And actually, we'll start doing actual chemical reactions next time. In the meantime, I guess we'll all just go. I'll see you all later. Okay, sorry. Let me get my camera. Battery lifetime after all. A